Hey, welcome. Today, we're going to pull back the curtain on a kind of invisible magic that honestly powers so much of our modern world. It's the secret sauce that lets factory robots and massive machines move with just incredible precision. And it's hiding right out in the open.
Right, so think about a robotic arm on an assembly line, or maybe a giant conveyor belt system. They move with perfect timing, perfect strength, and they start and stop on a dime. But here's the real puzzle. A lot of them do all this without any physical sensors on the motor to tell them how fast they're going or even what position they're in. So how in the world do they know? It's not magic, but it is seriously clever. So, to really appreciate just how revolutionary this sensorless stuff is, we first have to take a quick look at the old way of doing things. It was, a much simpler, but also a much clunkier way to control a motor's speed.
Okay, so the old method was pretty straightforward. Basically, an induction motor's speed is directly tied to the frequency of the electricity you feed it. You want it to go faster? You just crank up the frequency. Slower? You lower it. This is called V/F control. And yeah, it works. But as we're about to see, it's kind of like using a sledgehammer for a job that needs a scalpel. This quote right here, it really gets to the heart of the problem. See, you can't just change the frequency on its own. You have to perfectly balance the voltage along with it. If you don't, the magnetic forces inside the motor, the very things that create the motion, they just go haywire. This kind of crude approach really struggles to deliver precise twisting force, or torque, especially when you're starting up or trying to run slowly with a heavy load. And wow, the difference is just night and day. I mean, look at this. Simple VF control, you get low precision. And check out that second row. The torque at low speed is just plain poor. It's not very efficient either. But then you look at sensorless vector control and everything is just better. High precision, excellent torque right from a dead stop, and way higher efficiency. It is a total game changer. So how did we make the jump from that brute force method to this new era of really intelligent control? Well, the answer is in a breakthrough called sensorless vector control. It's a method that, for all intents and purposes, teaches the motor's controller how to think. So instead of just telling the motor, hey, go faster, sensorless vector control lets the drive, which is like the electronic brain, understand what's happening inside the motor. It calculates the motor's exact state in real time and then directly commands the specific magnetic forces, the vectors, that produce that powerful twisting motion. And that's the real magic here. It's not just commanding speed, it's commanding the very forces that create the speed. All right, this is the core of it all. How does the drive know the motor's position and speed without a sensor? Well, it does it by creating a perfect mathematical simulation, a model of the motor, right inside its own digital brain. Essentially, it builds what we call a digital twin. So here's the four-step dance. First, the drive monitors the electricity flowing into the motor with incredible precision. Second, it uses a really sophisticated mathematical model that is specific to that exact motor. Third, it predicts how the motor should be behaving based on its recent workload and even its temperature. And finally, with all that info, it performs lightning-fast calculations to know exactly what the spinning part of the motor is doing at any given millisecond. No sensor needed. Okay, so this is some seriously cool tech, but so what? Why does it matter in the real world? Well, this leap from theory to the factory floor has had a massive impact on what our machines are capable of. For instance, take a system for handling huge, fragile sheets of material. With sensorless vector control, the motors can start up smoothly even under a really heavy load and maintain a perfect, constant speed. This prevents any jerks or vibrations that could totally shatter the product. It delivers high torque, but does it gently. Or what about a giant industrial washing machine? This technology is what allows the very same motor to turn a super heavy waterlogged drum slowly and gently for the wash cycle and then ramp up to an incredibly high speed for the spin cycle. That kind of versatility is only possible because the drive has precise control across a massive range of speeds. So let's just sum up the benefits here. You get smooth, powerful control even at super low speeds. You get a huge, usable speed range from just one motor. You get automatic motor protection because the drive is always monitoring the current, so it acts like a built-in safety switch. And this is a big one, you get significant energy savings because the drive only uses the exact amount of power needed for the job and not a drop more.
So you can see, this is way more than just a better motor controller. This is a fundamental shift in how we build and interact with pretty much all of our machines. That mathematical model inside the drive, it isn't just a bunch of numbers. It's a dynamic, real-time digital twin, a perfect virtual copy of the physical motor. The drive gets that incredible precision by controlling its virtual twin, and the real motor just follows along perfectly. It's a really profound concept when you think about it, and it opens up a whole new world of possibilities.
And that really brings us to our final thought. We've basically given the humble electric motor a digital mind. We've made it smarter, more efficient, and more precise than we ever thought possible, all without adding a single physical sensor. So the question I want to leave you with is this: what happens next? What can we build when every single motor that moves our world has its own digital twin, thinking and adapting in real time?